Hello everyone. Today we're gonna give a last lecture about classification and so recall what we learned in last class. Last class we talked about the constructions of the multivariate normal distribution. We introduced if we have the random vector, you can think this is the D features. It follows D-dimensional normal distribution with location parameter mu and the variance covariance matrix sigma. And the PDF of X is given by, to simplify our notation, we first introduce the quadratic forms. For example, if we have the X is a vector, so X minus the mu, the location parameter transpose sigma inverse X minus mu. Okay, and another function is called just the exponential transformation, e to the power, maybe we can use this q, e to the power negative q over 2. So and multiply some normalization constant. Normalization constant is given by 1 over square root. It's too much space here. Maybe I can write on here. So nq is a function exponential to the power negative q over 2. So this function is basically a decreasing, monotone decreasing, non-increasing function, decreasing function. And we also need some normalization constant, 2 pi, okay, to the power d, and the determinant of the covariance matrix. And then we can have the density of the multivariate normal distribution is given by, it's just the composition of two functions. It's n q x. And the last class we also introduced eigen decomposition. So if this sigma is a covariance matrix, then this any symmetric matrix can be written as the eigen decomposition. So EI decomposition. So any symmetric matrix can be written as orthogonal matrix where each column is an eigenvector and times the diagonal matrix lambda. Maybe it's better to use lambda. Okay, where this lambda is a diagonal matrix with the diagonal elements to be sigma 1 square, okay, sigma d square, 0, 0. Okay, and this V matrix is a matrix. With eigenvectors of sigma. Okay, with eigenvalues for eigen sigma 1 square sigma d square. Okay. Last class we also introduced although the notations is a little bit complicated, but we introduced where this comes from. And actually this gives a way to generate normal distribution. So simulation for normal distribution. Okay. Actually, I will show you this plot here. Remember in our last class we talked about if we start from the z1 z2 plane. Okay, so this plot shows the contour plot of the function z, which equals to the norm of z square. Okay, and we want this contour plot as right circles, right? Circles, but we after water transformation we can get this ellipse. The transformation is we can get apply the sigma 1/2. The covariance matrix take the square root times z. Okay, we get x. So this transformation gives us the so this function of the norm square becomes the function of fx, or we can use qx, which equals to the quadratic forms. Actually, if you do the transformation plus mu, okay, so you can get the quadratic form. This is x minus mu transform sigma inverse x minus mu. Okay, and then after we get this quadratic form function, we apply to the exponential function. Okay, that's also the function the example we showed you last class. Okay, once you have this quadratic form function, okay, and then you apply to this exponential function. Exponential function is just the k times to power e to power negative q/2, right? So this is a decreasing function. So if you have this originally, if you have this ellipse form with contour plot looks like this. So this center part is the minimum point. So this is the minimum. But after this transformation, monotone decreasing transformation, so the minimum point becomes the peak. Okay. So that's where we simulate the normal distribution. So in other words, to simulate data from the normal random variable, you can start with the independent normal variables. So for example, step 1, simulate z1 from standard normal random variable 0, 1, z2 from the standard normal random variable. Okay, these two are univariate random variables, and z1, z2 are independent. And now you pick a correlation matrix sigma. Okay, and then you apply this transformation. So you have the shifting, location shifting sigma half, and multiply this z1, z2. Okay, and then you get x1, x2. So this x1, x2 will follows the normal distribution with average mu variance covariance matrix sigma. So that's the first step, second step. So this give us, so this is how we construct the multivariate normal distribution. And to apply the multivariate normal distribution for the classifications, we need to introduce the so we will apply multivariate normal random variable distribution to quadratic discriminant analysis and linear discriminative analysis. Okay, recall in the last two lectures, I think we introduced the in the lecture 7 we introduced a very special case. So in this case, we assume all the random variable follows the same scalar variance sigma square for the quadratic discriminant analysis. And for the linear discriminant analysis, we further assume each class also shares the same scalar variance. But in today's lecture, we assume we're gonna introduce the most general format of the quadratic discriminant analysis with very general covariance sigma square. So this is a matrix, not sigma square scalar. Not a scalar. Sigma square, and that introduced in lecture 7. Okay. So before we even introduce before even we apply the normal distribution to the quadratic QDA and LDA, we need to know how to, for each given class, how do we estimate this mu and sigma. Actually, the idea is very similar to the scalar case. We're gonna apply the maximum likelihood estimation. So maximum likelihood estimation for general multivariate Gaussian distribution. Okay. So suppose, so the assumption here we have here is we have the training data set, which is x1, xn, n data points, and class label class label. And the class variable y1, yn, okay. And in class C, we assume there are nc. So in class C, suppose we have like only two classes. One is the class C and one is not class C. Okay. And for each of the class, or even for the multi-label case, we have the label 1, label 2. Okay, but let's assume for each class C, we assume NC is the number of the points in our sample in class C. Okay. Again, we want to fit the normal Gaussian distribution that maximize the likelihood of generating the training points in a specified class. And here, the derivation is very similar to the UNIVARD case. And the derivation is a little bit more tedious, and I will give you a result here. If you wanted to know the derivations of these estimators, you can go to the class multivariate analysis. But here we just give you the estimators for the covariance matrix. So the covariance matrix can be estimated by 1 over NC. So the MLE means the maximum likelihood estimator of sigma. Variance covariance matrix is given by summation of I such that the labels for this summation is over all the samples with labels in the class C equal to C. Okay, and we for each point we need to subtract from the this is class average. Okay, and xi minus mu c hat transpose, and this is a d times 1 vector, and this transpose is 1 times d, so therefore this is the d by d matrix. So this is the estimators for this matrix. So this is called the conditional covariance. Okay, and mu hat c is just the sample mean. For all points in class C. Okay, and also we also need to estimate the prior pi c. We wanted to know in our population approximately how much proportion of the points falls into this class. So this is given by the number of the elements in the C divided by the total sample size. Okay, so here is one example of the MLE of the Gaussian distribution. For example, this is one. So now, for example, here we have two features. This is x1, this is x2. We have two-dimensional data, and we have the scatter plot. So each dot, each data point, it represents an observation with x1 value and x2 value. And this contour plot represents a fitted Biot normal distribution. Okay. So how do we find this best fitting contour plots? We are actually applying the MLE here. Okay. So this contour plot is given by this normal density with sigma and mu estimated this way. Okay. Also, last class we talked about the sigma variance. There are a few terminologies we introduced at the end of the last lecture, which is a positive definite. So this is positive semi-definite. Positive semi-definite. Because remember the positive definite means all the eigenvalues are positive. Semi-definite means positive or equal to 0. So in this case, and we know that when we construct this covariance matrix, we know the eigenvalues are just the variance for each variable. Okay, so as we can see here, the variance for the first normal distribution is not 0, and the normal distribution of second, maybe let me draw a little bit better graph here. Okay, so we have the second variate, the variance is also not 0. Okay, this is sigma 1 square. Okay, so but this is not always positive definite. If there are some 0 eigenvalues, we cannot, this won't be useful. Okay, so if some eigenvalues, if some eigenvalues of sigma hat c are 0, okay, we don't have very well defined the densities for this multivariate normal distribution, and the classification given by the quadratic discriminant analysis will not work. So the fix is we can try to fix it by eliminating the 0 variance dimensions. In the homework, I will give you one exercise about this problem, because this is estimate from data. Anything could happen, right? So, okay, and this is the MLE for the multivariate distribution. Okay, and these are the MLEs we need for the quadratic discriminative analysis. And for the linear discriminant analysis, actually the only differences is for the linear discriminant analysis, we assume sigma variance covariance matrix are identical across all classes. all classes. Okay, and therefore the MLE for this case will be a little bit different. So this is, so for LDA, we can estimate this is given by, so for each of the class, yi equals to C, class C, and xi minus mu hat C, xi minus mu hat C transpose. And you find this one across every class C, and you take the average over all the sample size. This is called pooled within class covariance matrix. So here is one example. If we have the two features again, we have the x1, x2. Okay, suppose now we have two class of labels. First one maybe here, and then maybe the second class is here. So this first part, inside the summation, this estimates the variance for each class. So this is called within class covariance part. So this is within covariance part. This means the covariance within each class. Each class. Okay, and then you find this within each class, and then you pull them together. Okay, you have this first variance, second variance covariance. You put them together and you take average. Usually this has better precision than the first one. Okay, and in the LDA, because we assume there's only one sigma variance covariance matrix, and this is the formula we use. Okay, I will continue in next video.